Welcome. Take a moment to settle in without trying to find the perfect position. Turn the volume down to the point where my voice is only just audible, a little below what would be comfortable in daylight. Nothing that follows needs to be remembered or understood or followed to the end. You can fall asleep at any point and you will not miss a thing. Tonight we are going to talk about gravity, slowly, without hurrying. The oldest evidence that human beings paid close attention to falling is not written down at all, but built. Long before anyone tried to explain why a stone dropped from the hand goes downward rather than sideways, masons and surveyors had learned to use that tendency as a tool, hanging a small weight from a cord and letting it settle until it hung motionless, and then treating the line of that cord as the standard against which walls and columns and door jambs were judged. The plumb line is a device that takes the fall of a weight and freezes it, and in doing so, it makes visible a direction that has no other marker. Since the horizon can be seen and the stars can be sighted, but the vertical exists only where something heavy is allowed to hang. Egyptian builders used such lines, and small plumb bobs of stone and metal have been recovered from tombs and workshops, along with the wooden squares and straight edges that went with them. One arrangement joined two arms in a shape rather like the letter A, with a cord and weight dropped from the apex, and a mark scratched on the crossbar, so that a mason could set the frame against a face of stone and read from the position of the cord whether the surface stood true or leaned. Another used a shallow trough of water, since a still liquid finds its own level, for the same reason that the weight finds its own line, and the two instruments together, the hanging cord and the resting water, gave the two references that all monumental building needs, the upright and the flat. What those builders had was not a theory of weight, but a working knowledge of it, and the working knowledge was considerable. They knew that a heavy block will slide down a slope if the slope is steep enough and will stay put, if it is not, and that the effort of dragging a load up a ramp is traded against the length of the ramp, and that a stone set slightly out of upright will settle and crack the courses above it, and that the pressure at the base of a wall grows with everything piled on top. The pyramids and the temple pylons are, among other things, long arguments about the behavior of heavy things, worked out in the only language available, which was trial, correction, and the accumulated habit of many generations of workshops. Weight also entered the earliest recorded arithmetic of trade. In Mesopotamia, the balance beam, with a pan hanging from each end, became the instrument that settled accounts in silver and grain and wool, and a system of standard weights grew up around it, cut in stone, often in the shape of a resting duck or a small loaf, and marked with the quantity they represented. The units were arranged in the sexagesimal manner that runs through Babylonian mathematics, with 60 of the smaller unit, the shekel making the minor and 60 minas making the talent, and temples and palaces kept reference weights against which the weights in use could be checked. Here heaviness became a number rather than a sensation, and it did so for reasons that had nothing to do with natural philosophy and everything to do with the need to be sure that a payment had been made in full. The balance carried a further implication that was not lost on the people who used it. It weighs by comparison rather than by feel, setting the unknown against the known and waiting for the beam to come level, and it therefore turns weight into a quantity that can be added, divided, and carried across from one commodity to another. Egyptian funerary papyri give the balance a moral office as well, showing the heart of the dead placed in one pan against a feather in the other, with a scribe recording the outcome, which suggests how thoroughly the instrument had entered the imagination of a society that used it daily in the marketplace and the granary. The imagery is religious, but the mechanism inside it is the same mechanism, and the assumption behind the picture is that heaviness is something real and measurable that belongs to a body and can be set against the heaviness of anything else. Babylonian scribes also computed with heavy things in a more abstract way, working out on clay tablets the volumes of earth to be moved for a canal or a rampart, the number of bricks needed for a wall of given dimensions, and the labor of a given number of workmen over a given number of days. Their astronomical tablets, kept over centuries, recorded the risings and settings of the moon and the planets, and eventually predicted them with arithmetic schemes of considerable subtlety, without ever proposing that anything pulled on anything else. The sky was described as a pattern of recurrences to be tracked, and the fall of a stone belonged to the ordinary world of building and carrying, and there was as yet no reason for anyone to suspect that the two subjects had anything to say to each other. The habit of asking why heavy things fall, rather than how to use the fact that they do, appears in the Greek cities of Ionia and southern Italy in the centuries when philosophers there began to look for underlying substances and underlying causes. Their questions were shaped by a difficulty that seems small and turns out to be large. If the Earth is a body sitting in space, then it is not obvious what holds it up. And every account of falling must also account for the Earth's own position. Thales is reported to have said that the Earth rested on water, floating like a piece of wood, and Anaximander proposed instead that it stayed where it was because it stood at the center with nothing to prefer any one direction over another, being equally distant from everything and therefore having no reason to move at all. Anaximenes described it as broad and flat and supported by air beneath it. Those answers differ, but they share a way of thinking about heaviness that later writers would develop at length, which is that weight is a tendency toward a place rather than an attraction between bodies. In this view, a stone does not fall because the earth draws it, but because the stone belongs at the bottom and is out of place until it gets there, and the earth itself sits at the bottom of everything, for the same reason, gathered at the center because that is where heavy matter accumulates. Empedocles set out 4 roots of all things: earth, water, air, and fire, and the ordering of those 4 by heaviness, with earth lowest and fire highest, gave a rough scheme that matched a great deal of everyday observation. Since soil sinks in water, water sits under oil, air rises through water in bubbles, and flame goes up. Plato, in the dialogue on the making of the cosmos, put the matter in terms of like moving toward like, arguing that in a spherical universe there is no absolute up or down in the way that ordinary speech assumes, and that what we call downward is simply the direction toward the greater mass of kindred material. The atomists took a different road. Leucippus and Democritus held that everything is made of indivisible particles moving in a void, that these particles differ in size and shape, and that the heaviness of a body has to do with how much solid matter it contains and how little empty space, an account which locates weight in the composition of a thing rather than in its yearning for a station. By the middle of the 4th century before the Common Era, then, there existed a set of overlapping ideas about falling that had never been tested against careful measurement. because measuring a fall requires the ability to measure short intervals of time, and no one yet could. Water clocks and sundials divided the day, and the balance divided weight with real precision, and the plumb line held the vertical steady. But the moment of a stone's descent was too brief for any of them. What was available instead was a great store of practical familiarity from quarry and building site and marketplace, and a young tradition of argument that had begun to organize heaviness into a scheme of elements and natural positions, waiting for the systematic treatment that would fix it in place for a very long time. Aristotle came to these questions with a temperament unlike that of the men who had gone before him, because where Plato preferred to reason about ideal forms and the atomists about invisible particles, Aristotle wanted an account of the world that began with what could be seen and handled, and that explained the ordinary behavior of ordinary things without appealing to entities no one could observe. He had spent something close to 20 years in Plato's academy in Athens, and afterward travelled in Asia Minor and on the island of Lesbos, and served for a time as tutor to the young Macedonian prince who would become Alexander, before returning to Athens to found his own school in a grove outside the city walls. There he lectured, and his students took notes, and from those notes came the treatises we now read, among them the 8 books of the Physics and the 4 books of On the Heavens, in which the falling of a stone and the turning of the stars were treated as parts of a single connected subject. The starting point was a definition of motion broad enough to hold almost everything that changes. For Aristotle, motion in the widest sense included growth and decay, the warming of water, the reddening of a fruit, and the alteration of a thing from one quality to another, and change of place was only one variety among several, though it was the variety he examined most closely. Every motion he held required something moved and something moving it, and it was to be understood by asking what the thing was for, what it was made of, what shape or form it had taken, and what had set it going. This fourfold way of asking questions ran through all his work, and when he turned it upon a falling stone, it produced an answer that had less to do with pushing and pulling than with the nature of the stone itself. There were, in his account, 4 elements in the region below the heavens, and each had a natural place and a natural motion belonging to it. Earth was heavy without qualification, and its natural motion was toward the center of the cosmos, which is also the center of the earth. Water was heavy as well, though less so, and it came to rest upon the earth. Fire was light without qualification, and its natural motion was upward, away from the center and toward the outermost boundary of the sublunary world. Air was light in a lesser degree and settled beneath the fire and above the water. Lightness here was not merely a smaller quantity of weight, which is worth pausing over, because in Aristotle's scheme, fire does not rise because something heavier displaces it, but because rising is what fire does by its own nature, in the way that falling is what earth does. Heaviness and lightness were 2 distinct positive tendencies rather than the 2 ends of one scale. Arranged in this way, the elements formed a set of nested shells, with earth gathered at the center, water above it, air above that, and fire in a sphere touching the innermost of the heavenly spheres. The scheme accounted for a good deal of everyday experience with very little machinery. It explained why a clod of soil dropped into a pond sinks, and why a bubble in that same pond rises, why flames lean upward whichever way the candle is tilted, why oil floats upon water and water rests upon a bed of stones. It explained why the earth is round, since if every part of the earthy element presses toward one central point, the mass so formed must take a spherical shape, and Aristotle set this reasoning beside the observations that the shadow cast on the moon during a lunar eclipse has a curved edge, and that new stars come into view as a traveler moves south. Above the sphere of fire in this account, the rules changed entirely. The heavens were made of a fifth substance, ungenerated and unchanging, whose natural motion was neither toward the center nor away from it but around, in perfect circles that could continue without beginning or end. Because circular motion returns upon itself, it needed no starting point and no terminus, and so the celestial bodies could turn forever without exhausting any tendency, while the four terrestrial elements, whose natural motions ran along straight lines, must always come to rest once they reached the place that belonged to them. The division was sharp, and it carried a consequence that would matter greatly to later astronomy. Whatever happened in the sky could not be explained by the physics of stones and flames, and whatever happened on Earth could not be explained by the physics of the stars. Motion that was not natural, Aristotle called violent or forced, and it included every displacement produced by an external agent. The cart drawn along the road, the stone thrown from the hand, the water raised in a bucket from the well. Such motions lasted only as long as the mover acted, and here the system met a difficulty its author acknowledged and worked at without ever fully settling. A stone leaving the hand continues to travel after the hand has stopped touching it, and since Aristotle held that nothing moves without a mover in contact with it, something must be doing the moving. His suggestion was that the air itself carried the motion forward, having received from the thrower a power to move that it passed along from one portion to the next, so that the projectile was pushed by the medium through which it flew. Later readers found this the least persuasive part of the whole structure, and it was precisely there that the first serious cracks would appear. The medium played another role as well, for it resisted. A body falling through water descends more slowly than the same body falling through air. And from this plain observation, Aristotle drew a general relation in which the speed of a fall depends on the weight of the body and on the density of the stuff it passes through, so that greater weight brings greater speed and thicker medium brings less. Read strictly, the rule implies that of two stones released together, the heavier reaches the ground in less time, in some proportion to their weights. It also supplied one of his arguments against the existence of empty space, since in a void there would be nothing to resist at all, and a falling body would then move with no determinate speed, which he regarded as absurd. The void was ruled out on several grounds, and this was among them. Whether Aristotle himself ever dropped two unequal weights from a height is not recorded, and the question of how much testing his physics rested upon has been argued over ever since. What is clear is that the account was assembled from a very wide survey of common experience rather than from measurement, and that its author was in other domains a patient and exact observer, dissecting animals and describing the development of the chick in the egg, with a care that later naturalists admired. In the study of motion, the instruments were simply not there, and the difficulty was not laziness, but the absence of any clock that could divide a second. The framework then traveled, and its travels are much of the reason it endured. Aristotle's successors at the Lyceum preserved and extended the texts. The scholars of Alexandria copied and commented on them. The late antique commentators, writing in Greek several centuries into the Common Era, worked line by line through the physics and on the heavens, and in doing so both transmitted the doctrine and recorded objections to it. From Greek, the treatises passed into Syriac and then into Arabic, and in Baghdad and later in Cordoba, they became the foundation of a philosophical tradition that produced commentaries of great length and subtlety. From Arabic, and afterward directly from Greek, they passed into Latin during the 12th and 13th centuries, arriving in the new universities of Paris and Oxford and Bologna at exactly the moment when those institutions were deciding what a curriculum should contain. For a time, the natural books were regarded with suspicion by ecclesiastical authorities at Paris, and their teaching was restricted. But within a few decades, they had become the ordinary matter of the arts course, read, disputed, and examined upon, and their author was referred to simply as the philosopher, as though no other were needed. A student in the Latin West learned that earth seeks the center, that fire seeks the periphery, that the heavens turn in circles of a different substance, and that heavier bodies fall faster than light ones. The scheme was coherent, it agreed with a great deal of ordinary observation, and it was taught, in one version or another, for something close to 2,000 years. The objections began early, and they began inside the tradition rather than outside it. Among the commentators of Alexandria in the 6th century of the Common Era was a Christian scholar named John Philoponus, who wrote at length on the physics in the ordinary manner of a teacher explaining a set text, and who then, at certain points, set the text aside and disagreed with it. He disagreed about the void, arguing that motion through empty space was not the absurdity Aristotle had made it out to be, since a medium does not enable motion but hinders it, so that removing the medium would not abolish speed but merely leave it unimpeded. And he disagreed about the rule of falling on the grounds that it did not survive being looked at. If one takes two weights, one many times heavier than the other, and releases them from the same height at the same moment, the difference in their arrival is small, and nothing like the difference in their weights. The remark is brief, buried in a long commentary, and it is not accompanied by any record of careful measurement, but it is one of the earliest surviving statements that the doctrine of proportional speeds fails against ordinary experience. Philoponus also proposed a replacement for the awkward Aristotelian account of the thrown stone. Instead of the air pushing the projectile along, he suggested that the thrower impresses something into the body itself, an incorporeal motive power that travels with it and is gradually spent, so that the stone flies because it carries within it a diminishing supply of motion. This idea, in one form or another, would be restated for the next 1,000 years by writers who had never read him, and it is the seed of what the Latin schools would eventually call impetus. His criticisms did not overturn anything in his own century. They did, however, enter the stream of transmission, and when the Greek treatises passed into Arabic, the objections traveled with the doctrine. In 11th century Persia, Ibn Sina, known in the Latin West as Avicenna, took up the question of the projectile in his own encyclopedic works and gave the impressed power a name, male, meaning inclination or leaning. He treated it as a real quality lodged in the moving body, distinguished varieties of it, and reasoned that in the absence of any resisting medium, an impressed inclination would not fade at all, so that the body would continue in motion without end. The conclusion was not offered as a description of the world, since the world as he understood it contained no such empty stretches, but as a consequence of the definition, and it stands as one of the clearest medieval statements of the persistence of motion. In Baghdad in the following century, Abu al-Barakat al-Baghdadi extended the analysis to falling itself. If a heavy body accelerates as it descends, and if motion requires an impressed inclination, then the acceleration must come from inclination. Being impressed continuously, each new increment added to what is already there, so that the body gathers motion as it goes. This is a genuine advance in the description of free fall. It makes acceleration the natural consequence of a persistent cause rather than an oddity requiring separate explanation, and it locates the cause in the heaviness of the body acting at every instant rather than only at the start. Elsewhere in the Arabic-speaking world, the argument turned back to the mathematics of speed. In Spain, Ibn Bajjah, whom Latin readers came to know as Avem Parce, considered the relation between the moving force, the resistance of the medium, and the resulting speed, and proposed that resistance should be subtracted from the driving power rather than divided into it, which has the consequence that a body in a void would move with a definite finite speed rather than an instantaneous one. Ibn Rushd of Córdoba, the great commentator whom the Latins called Averroes, recorded this view in order to argue against it, and by recording it, he carried it westward, since his commentaries were among the first of these works to be translated into Latin and were read with enormous attention in the universities. A good deal of what the schoolmen of the 13th and 14th centuries knew about the alternatives to Aristotle they knew from the writings of men who had rejected those alternatives. By the middle of the 13th century, the natural books, with their Greek and Arabic commentaries, were the standard reading of the arts faculties at Paris and Oxford, and the method of teaching them almost guaranteed that they would be questioned. Instruction preceded by disputation, a question was posed in a fixed form. Arguments were assembled on both sides, distinctions were drawn, and a determination was given. The habit of the exercise was to press every claim to its limit and to ask what would follow if some condition were altered, and this habit was applied to falling bodies as readily as to anything else. In Paris in 1277, a long list of propositions was condemned by the bishop. Among them, the assertion that God could not move the heavens in a straight line, because that would leave a vacuum behind. The condemnation had the effect of licensing a certain kind of speculation, since theologians were now obliged to allow that God could do such things, and the question of what motion would look like in a void, once forbidden as absurd, became a legitimate topic for the schools. At Oxford, in the second quarter of the 14th century, a group of scholars associated with Merton College turned the analysis of motion into something close to a mathematical discipline. Thomas Bradwardine wrote a treatise on the proportions of speeds, in which he proposed that speed depends not on the simple ratio of force to resistance, but on a compounding of that ratio. A rule constructed so that when force and resistance are equal, no motion results, which the Aristotelian formulation had failed to secure. William Heytesbury, in a work written for undergraduates learning to untangle sophisms, drew the distinction that mattered most: the difference between the description of a motion and the search for its cause. One could speak precisely of how fast a body moves at a given instant, and of whether its speed is uniform or changing, and of whether the change itself is uniform, without saying anything at all about what makes it move. Richard Swineshead and John Dumbleton worked through the same material at great length, and the four of them are remembered together as the Oxford calculators. Out of this work came the result that has proved the most durable. If a body moves with a uniformly increasing speed for a given interval of time, it covers exactly the same distance as it would have covered moving steadily for that same interval at the speed it had at the middle instant. The rule is now usually called the mean speed theorem, and the Merton scholars proved it by the arithmetic of proportions. It was stated as an abstract truth about a kind of motion that might or might not occur in nature, and the men who proved it did not connect it to falling stones, but the statement was made, written down, copied, and taught. In Paris, the same questions were pursued with a different emphasis. Jean Buridan, Master of Arts and twice rector of the university, revived the impressed power and gave it the name by which it is remembered: impetus. He treated it as a lasting quality, proportional to the speed of the body and to the quantity of matter in it. And he argued that it does not decay of itself, but only through the resistance of the medium and the contrary tendency of the body's own heaviness. A grindstone spun and then left alone continues to turn for a long while, he observed, and a thrown lance sharpened at the rear flies, as well as one blunt behind, which it should not if the surrounding air were doing the pushing. He used impetus to explain the acceleration of falling bodies, gravity impressing a fresh increment at every moment upon what is already present. And he suggested that the heavens might turn on an impetus given at the creation and never diminished, there being nothing above to resist it. Buridan's pupil Nicole Oresme, later Bishop of Lisieux, took the Oxford theorem and gave it a form that could be seen. He represented equality by a geometrical figure, laying out time along a horizontal line and the intensity of the motion as vertical heights raised upon it, so that a uniform speed became a rectangle and a uniformly increasing speed became a triangle, and the equality of the two distances became the plain geometrical fact that the triangle and the rectangle on the same base, with the rectangle's height equal to the triangle's middle height, have the same area. He also wrote, in French, a long commentary on Aristotle's book on the heavens for the King of France, in which he assembled the arguments for and against a daily rotation of the earth and concluded that no observation then available could settle the matter, since all the appearances would be the same either way. Having said so, he declared his adherence to the common opinion. The reasoning outlasted the conclusion, and both the diagram and the rule waited, in manuscript and later in print, for someone to hold them against a rolling ball. Galileo Galilei was born at Pisa in 1564, the son of a musician and theorist of music who had himself argued, in print, that the ear and the string should be consulted before the authority of ancient writers on harmony. The son was sent to the university of his birthplace to read medicine, which was the profession that paid, and he left it without a degree, having been drawn aside by a Florentine mathematician named Ostilio Ricci, who taught him Euclid, and, more consequentially, the works of Archimedes on floating bodies and on the equilibrium of planes. From Archimedes, he took a habit of mind that would mark everything he later wrote, which was the habit of treating a physical situation as a geometrical one, stripping away what could not be measured until something remained that could be stated as a proportion. He earned a living for a while by private teaching, invented a hydrostatic balance for determining the composition of alloys, and in 1589 obtained the chair of mathematics at Pisa, a poorly paid post that he held for 3 years. During those years, he composed a treatise on motion which he never published and which survives among his papers. In it, he attacked the Aristotelian account directly, arguing that the speed of a falling body depends not on its weight alone, but on the difference between its density and the density of the medium through which it moves. A formulation that owes much to Archimedes and something to the medieval critics, and which is wrong, though wrong in a productive direction. He also noticed, and recorded with evident puzzlement, that when 2 balls of different material are released together, the lighter sometimes moves ahead at the start before the heavier overtakes it, an observation that does not fit any simple rule, and that he never fully explained. He was not alone in dropping things from heights in those decades. In Delft, a few years earlier, the engineer and mathematician Simon Stevin and his acquaintance Jan Cornets de Groot had let 2 lead spheres of very different weight fall together some 30 feet onto a wooden board below, and reported that the sound of the 2 impacts arrived as a single knock. The story of Galileo dropping weights from the leaning campanile at Pisa comes to us from Vincenzo Viviani, his last pupil and his first biographer, writing many years after his master's death, and Galileo himself never described such a demonstration in his own books. What he did give, decades later, was an argument that needs no tower at all. Suppose he had his spokesman say that a heavy body falls faster than a light one, and now bind the 2 together. The light one, being slower, should retard the heavy one, so the pair should fall more slowly than the heavy stone alone. Yet the pair is heavier than the heavy stone alone, and so by the same rule should fall faster. The supposition leads to 2 contradictory conclusions and must be abandoned. The demonstration that satisfied him was not a fall but a slow, controlled descent. He had a board some 12 cubits long, half a cubit wide and 3 finger breadths thick, into which a straight channel a little more than an inch wide was cut along its length, and this channel he lined with parchment, polished as smooth as could be managed, so that a hard, round, well-turned bronze ball would run along it without wobbling or catching. The board was raised at one end by a hand's breadth or 2, and the ball was let go from rest and allowed to run the whole length while the time was noted. Then the ball was released, not from the top, but from a quarter of the way down, or a half, or 2/3, and the times for those shorter runs were noted in the same manner, and each measurement was repeated many times over until the variation between trials had fallen to a small fraction of a beat. What the ball did was consistent and once seen simple. In each case, the distance traveled stood to the square of the time taken in a fixed ratio. Double the time, and the ball had covered 4 times the length of channel. Treble it, and 9 times. And the same held whether the board was tilted a little or a good deal, only the constant of proportion changing with the inclination. Stated in another way, if the descent is divided into equal intervals of time, the lengths run through in successive intervals stand to one another as the odd numbers, 1, 3, 5, 7, and so on without end. That rule, the odd number rule, is the same fact as the time squared rule, since the sum of the first so many odd numbers is the square of how many there are, and both were rules that the medieval calculators had reached by reasoning about intensities without ever bringing a ball to bear on the question. The timing was the difficulty, since no clock of that period could resolve fractions of a second. Galileo used water. A large vessel was filled and fitted with a narrow pipe at the bottom, and during each descent, the thin stream from the pipe was caught in a small glass. Afterwards, the water so collected was weighed on a delicate balance, and the weights, being proportional to the times, served in place of the times themselves. The method has the advantage of turning an interval that cannot be seen into a quantity that can be handled at leisure, and he claimed that repeated trials agreed with one another to within about 1/10 of a pulse beat. His surviving working sheets contain columns of figures and rough diagrams that show the labor behind the tidy propositions of the printed book. Having the rule, he needed a definition to place beneath it, and he chose the one the Oxford calculators would have recognized, that a motion is uniformly accelerated when it receives equal increments of speed in equal intervals of time. He considered the alternative, that speed grows in proportion to the distance fallen rather than to the time elapsed, and argued it away. From the definition, together with the geometry of intensities that Oresme had drawn as a triangle upon a line, the time-squared rule follows as a theorem, and the whole becomes a single connected piece of mathematics rather than a collection of measurements. He then supposed, without being able to prove it, that free fall is the limiting case of the inclined plane, as the incline is raised toward the vertical, and that the acceleration is the same for all bodies, whatever their weight, the observed differences belonging to the resistance of the air rather than to the fall itself. The swinging weight gave him a second instrument, and one whose regularity is easier to notice than to explain. He found that a pendulum of given length keeps very nearly the same period whether it swings through a wide arc or a narrow one, so that as friction and the air gradually reduce the swing, the beat does not quicken, that the period lengthens with the square root of the length, so that a pendulum 4 times as long beats half as often, and that the material and weight of the bob do not affect it. To make the last point, he hung 2 balls of equal size, one of lead and one of cork, on threads of equal length, set them going, and counted their swings together. The cork lost amplitude much faster, its motion dying away, while the lead was still swinging widely, and yet the two continued to arrive at the ends of their arcs in step, hundreds of oscillations later, without either gaining a beat on the other. He tied the pendulum and the plane together with a further observation. If the string of a swinging weight is intercepted by a nail fixed in the wall below the point of suspension, so that the bob is forced onto a shorter radius partway through its swing, it still rises to very nearly the same height as that from which it was released, and it does so wherever the nail is placed. Descent through a height confers exactly the speed needed to climb the same height again, whatever the path taken, and a ball rolling down one incline and up another will very nearly regain its level however gentle the second slope may be. From this it is a short step, though a step Galileo took only part way, to the thought that a ball set moving along a perfectly level and unresisting plane would neither gain nor lose speed and would continue as it was. He also treated the flight of a thrown body as 2 motions carried on at once, a uniform motion forward and a uniformly accelerated motion downward, indifferent to one another, and showed that the path traced by their combination is a parabola, from which he drew up tables for the ranges of shot at various elevations. All of this appeared in the discourses and mathematical demonstrations concerning two new sciences, dictated in his old age under house arrest at Arcetri after the trial of 1633, carried out of Italy and printed at Leiden in 1638, by which time its author had gone blind. As to what heaviness is and why bodies possess it, he declined to say, remarking that the present was not the occasion to inquire into the cause of the acceleration of natural motion, and that it was enough to have investigated and demonstrated some of its properties. While the descent of bodies was being measured on grooved boards in Italy, the motions of the heavens had already been submitted farther north to a discipline of a different kind. Tycho Brahe, born in 1546 into the Danish nobility, received from King Frederick II the small island of Hven in the sound between Zeeland and Scania, and there from 1576 onward he built Uraniborg, a house that was also an instrument, with walls oriented to the cardinal points, workshops for grinding and forging, a paper mill, and rooms for the assistants and students who passed through in a steady stream. When he found that wind and the movement of the building itself disturbed his sightings, he built a second observatory nearby, Stjerneborg, in which the great instruments stood in sunken chambers below ground level, sheltered from the weather and steadied by the earth around them. He had no telescope, for none yet existed in the form that would later be turned to the sky. What he had were quadrants and sextants and armillary spheres of unusual size, divided with unusual care, mounted so that they would not flex, and read by observers trained to estimate fractions of the smallest divisions. He compared his instruments against one another, recorded the errors of each, corrected for the bending of light near the horizon, and above all, he observed continuously, night after night, in every part of a planet's course, rather than only at the moments the older astronomy found convenient. The positions he recorded were good, in the best cases to 1 or 2 minutes of arc, which is roughly the width at which the unaided eye begins to separate two close points of light, and this was several times better than anything available before him. Among the planets, Mars received particular attention. Its path across the sky is the most awkward of the outer planets, its loops of apparent backward motion differing markedly in size from one occurrence to the next, its distance from the Earth varying more than that of Jupiter or Saturn, and its orbit departing further from a circle than any other then known except that of Mercury, which is hard to observe at all in the glare near the Sun. Tycho himself did not accept that the Earth moved. He proposed instead an arrangement in which the Earth stood still, the Sun circled the Earth, and the remaining planets circled the Sun, which reproduced the observed motions as well as the Copernican scheme did while leaving the Earth at rest. After a quarrel with the young king Christian IV, he left Denmark, and toward the end of the 1590s, he settled in Bohemia under the patronage of the Emperor Rudolf II, with his instruments and, more importantly, his decades of records. Johannes Kepler was born in 1571 at Weil der Stadt in Württemberg, studied at Tübingen, where the astronomer Michael Maestlan acquainted him with the Copernican arrangement and left him convinced of it, and took a post teaching mathematics at the Protestant school in Graz. There, in 1596, he published the Mysterium Cosmographicum, in which he proposed that the spacing of the 6 known planets was fixed by the 5 regular solids of Greek geometry. nested one within another between the spheres that carried the planets, each solid inscribed in one sphere and circumscribing the next. The scheme does not hold, and the discovery of further planets would have destroyed it in any case. But two habits of thought in that early book stayed with him for the rest of his life. He believed that the distances and speeds of the planets had reasons that could be found, and he had already noticed that the outer planets move more slowly along their paths than the inner ones, from which he inferred that whatever moved them proceeded from the sun and grew weaker with distance. Pressure on Protestants in Graz made his position there untenable, and after an exchange of letters and a first visit, he moved to Bohemia in 1600 to work with Tycho. The relations between the two were guarded, since Tycho parted with his observations reluctantly and in small portions, and he set Kepler to work on the orbit of Mars, a problem that had already defeated one of his senior assistants. Tycho died in October of 1601, and Kepler succeeded him as imperial mathematician, which placed the whole body of the observations within his reach, and involved him in years of negotiation with Tycho's heirs over the right to use them. The work that followed occupied the better part of a decade, and Kepler afterwards described it as his war with Mars. He began within the older framework, fitting to Tycho's data a circular orbit with the point of uniform angular motion separated from the geometric center. The arrangement inherited from Ptolemy under the name of the equant. By adjusting 4 parameters, he obtained what he called his substitute or vicarious hypothesis, and it reproduced the observed longitudes of Mars to within about 2 minutes of arc, which was as good as the observations themselves. It failed elsewhere. The latitudes came out wrong, and so did the distances of the planet from the Sun. And when he pressed the model against certain positions, it disagreed with the record by 8 minutes of arc. In an earlier astronomy, such a residue would have been absorbed into the general untidiness of observation. Kepler knew what Tycho's instruments could do, and he wrote that those 8 minutes, which it was not permitted to neglect, showed the way to a reform of the whole of astronomy. His method of attack was patient and indirect. To learn the shape of the orbit of Mars, he first had to know the orbit from which he was observing it. And so he used Mars itself as a fixed marker, taking pairs of observations separated by intervals of about 687 days. One Martian year, when the planet had returned to the same point in space, while the Earth stood elsewhere, and triangulating from these the varying distance of the Earth from the Sun. Having established the Earth's path, he turned back to Mars with the same technique, and obtained a set of distances and directions that no circle would accommodate. The curve was flattened at the sides, an oval rather than a ring, and he spent long stretches of labor on ovoid figures constructed from physical assumptions, filling hundreds of pages with arithmetic done by hand. 2 results emerged from that labor, and the second came after the first. He found that although the planet's speed along its path is not uniform, the line drawn from the Sun to the planet sweeps out equal areas in equal intervals of time, so that the planet moves quickly when near the Sun and slowly when far from it, in a proportion exactly compensated by the changing length of the line. Then, having approached and rejected the figure once already, he found that the curve was an ellipse, with the Sun not at its center but at one of its 2 foci. The 2 statements together fixed both the shape of the orbit and the timing of the motion along it, and they replaced the circles the epicycles and the equants that had carried planetary theory for 1,500 years. He published them in 1609 in a volume whose title announced a new astronomy founded upon causes, or a celestial physics set out in commentaries on the motions of the planet Mars from the observations of Tycho Brahe. The phrase about causes was not decoration. Kepler wanted a physical account of why the planets move as they do, and he built one from the materials available to him. He supposed that the sun turns on its axis and sends out from itself an immaterial emanation, a species of moving force, which spreads through the space around it and sweeps the planets along in the direction of the solar rotation. Because he pictured this force as spreading out within the plane of the orbits rather than in every direction through space, he took it to weaken in simple proportion to distance, in contrast to light, which he knew diminishes as the square of the distance because it spreads over a surface that grows in 2 dimensions at once. To explain why the distance from the Sun varies within a single orbit, he drew on William Gilbert's treatise on the magnet, published in 1600, and treated the planet as a magnetic body with an axis held in a fixed direction, so that as it went round, it presented first an attracting and then a repelling face to the Sun, and was drawn nearer and then pushed away. He also believed that matter possesses a natural sluggishness, an unwillingness to move which must be continually overcome, so that the removal of the driving force would bring a planet to rest. The idea that motion persists of itself was not yet his. In the long preface to the same book he set down, apart from his solar mechanics, a description of heaviness that reads differently from the rest. He wrote that gravity is a mutual affection between kindred bodies which tends to join them together, that heavy things do not seek the center of the universe, but the center of the round body to which they belong, and that if 2 stones were placed anywhere in space beyond the reach of any third body, they would come together at an intermediate point, each approaching the other through a distance proportioned to the bulk of the other. He added that the waters of the sea are drawn by the moon, and that the tides are the visible sign of it. Galileo, who corresponded with him and shared his Copernicanism, thought this notion of a lunar pull on the ocean an occult fancy and would have none of it. A third regularity came later. On a day in the spring of 1618, working on the ratios he had pursued since youth, Kepler found that the squares of the periods of the planets stand in the same proportion as the cubes of their mean distances from the Sun, and after an error in the calculation and a return to it some weeks afterwards, he satisfied himself that the relation held for every planet then known. He published it in 1619 in The Harmony of the World, embedded among speculations on musical intervals and the proportions of the heavens that he valued at least as highly. In 1627, after years of interruption by war, by exile from one town after another, and by the trial of his mother on a charge of witchcraft, from which he worked for years to have her released, he brought out the Rudolphine tables, computed from the elliptical theory, which reduced the errors of planetary prediction by a large factor, and by which astronomers of the following generation successfully caught Mercury and then Venus in the act of crossing the face of the Sun. Kepler died at Regensburg in 1630, in the course of a journey to collect money owed to him. What he left was a set of 3 statements of great accuracy whose causes remained unsettled. The sweeping solar force and the magnetic axes did not survive, and later readers passed over them with some embarrassment. the insistence that the sun acts physically upon the planets, that the action weakens with distance, and that heaviness is a mutual tendency of bodies toward one another rather than a striving toward a privileged point in space, did survive, and so did the third relation between periods and distances, which contains within it, though not in a form Kepler could read, the particular manner in which such an action must diminish. 12 years after Kepler died at Regensburg in the winter of 1642, a child was born prematurely at Woolsthorpe in Lincolnshire, in a farmhouse of grey stone belonging to a family of modest yeoman standing, and was not expected to live through the first weeks. His father had died some months before his birth. He was sent to school at Grantham, taken out of it for a period to learn the management of the estate, which he managed badly and without interest, and returned to it at the urging of the schoolmaster and an uncle, and in 1661 he entered Trinity College, Cambridge, as a sub-sizar, which is to say a student who paid part of his way by service. The mathematics he found there was the ordinary university mathematics of the day, and he set it aside fairly quickly in favor of reading on his own, working through Descartes and the algebraists of the previous generation, filling notebooks with problems and with the beginnings of methods that were not yet in any book. In the summer of 1665, the plague reached Cambridge, and the university sent its members away and closed for the better part of 2 years. Newton returned to Woolsthorpe and worked there in a solitude that suited him, and in the course of those months and of the intervals of residence between them, he arrived at the method of series and fluxions that became his calculus, at the composition of white light from colored rays, and at the first version of what he later called his thoughts on gravity extending to the orb of the moon. He was in his early 20s. Almost none of it was published for many years, and some of it not in his lifetime, and the long delay would later cost him a great deal of energy in quarrels over who had reached what first. The apple belongs to this period, or at least Newton in old age placed it there. He told the story more than once to visitors in the last years of his life, among them the antiquarian who wrote it down after an afternoon in the garden, and the account is consistent in its outline. He had been sitting in the orchard at Woolsthorpe when an apple fell, and the fall set him considering why an apple should always descend perpendicularly to the ground rather than sideways or upward, and whether the power that drew it down might not reach far higher than the tops of trees, as high as the moon, and if so, whether it might be the very thing that keeps the moon from flying off in a straight line. There is no reason to doubt that something of the kind happened, and no reason to make it more than it was. It was not a solution. It was the setting of two familiar things side by side, a falling fruit and a circling satellite, in the expectation that one law would cover both. What he did with the thought is more interesting than the thought. Taking the crude rule that a body moving in a circle presses outward in proportion to its speed squared and inversely to the radius, and combining it with Kepler's relation between the squares of the periods and the cubes of the distances, he found that the force holding the planets to the sun must fall off as the square of the distance from it. He then applied the same measure to the moon, whose distance was reckoned at about 60 times the radius of the Earth, so that the force there ought to be 1 part in 3,600 of the force at the Earth's surface, and he compared the resulting fall of the moon toward the Earth in a minute of time with the fall of a stone at ground level. The two figures agreed reasonably, though not closely, and he later said that they answered pretty nearly. The imperfect agreement came in part from the poor value he had for the size of the Earth, taken from a sailor's rough estimate of the length of a degree of latitude, and in part from a difficulty he had not yet resolved, which was whether a large sphere attracts a small body outside it, as though all its matter were gathered at its center. He put the papers aside for some years and turned to optics, to alchemy, to chronology, and to the interpretation of scripture, on which he wrote at length. What brought him back was correspondence. In the winter of 1679 and the following year, Robert Hooke, then Secretary of the Royal Society, wrote to him proposing that celestial motion be understood as a straight-line motion continually bent by an attraction toward a center, and suggesting that the attraction went as the inverse square. Though Hooke could not derive the consequences, the exchange was polite and then strained, and in the course of it, Newton solved the problem of the sphere, proving that a homogeneous sphere attracts an external body exactly as if its mass were concentrated at the center, which is what makes the comparison of apple and moon legitimate rather than approximate. He also demonstrated that an inverse square attraction, directed at a fixed point, produces orbits that are conic sections, and that the ellipse is the case of a body that does not escape. In August of 1684, Edmund Halley, younger than Newton by some years and already an accomplished observer, travelled to Cambridge to ask him a question that had been discussed without result in London: what curve a planet would describe under a force diminishing as the square of the distance. Newton answered that it would be an ellipse, said that he had calculated it and could not immediately find the papers. He worked the proof again and sent it to Halley in the autumn, along with a short tract on the motion of bodies in orbit, which was entered in the Register of the Royal Society. Halley, recognizing what he was looking at, urged him to expand it and to publish, and Newton, once engaged, did not stop for something close to 18 months, writing with an intensity that his servants and colleagues remembered afterwards, taking meals irregularly and sleeping little, and producing 3 books in Latin where a pamphlet had been asked for. The first book of the Philosophiae Naturalis Principia Mathematica lays down definitions of mass, momentum, and force, states the 3 laws of motion, and develops the geometry of orbital motion under central forces in a vacuum. The second treats motion through resisting fluids, and in doing so demonstrates that the vortices of Descartes, in which planets were carried along by a swirling subtle matter, cannot produce the motions that are actually observed. The third book, which Newton called the System of the World, applies the results to the heavens. The satellites of Jupiter and of Saturn, the planets about the Sun, the Moon about the Earth, all obeying one law in which every particle of matter attracts every other with a force proportional to the product of the masses and inversely proportional to the square of the distance between them. From that law he obtained the masses of the Sun and of the planets that have moons, the flattening of a rotating Earth, the precession of the equinoxes, the 2 daily tides, the irregularities of the lunar orbit, and the path of the comet of 1680, computed as a conic from observations that Flamsteed supplied at the Royal Observatory. Publication was not straightforward. The Royal Society had spent its printing funds on a lavishly illustrated history of fishes and had no money for Newton's manuscript, so Halley paid for the printing himself, corrected the proofs, managed the diagrams, and soothed the author. Hooke let it be known that he expected acknowledgement for the inverse square law, and Newton, angered, spoke of suppressing the third book altogether and had to be talked out of it by Halley, settling in the end for a grudging mention of Hooke, among others, in a scholium. The work appeared in the summer of 1687 in a printing of a few hundred copies, dense with propositions in classical geometrical form rather than in the analytical notation that Newton had himself invented, so that even sympathetic readers found it slow going. A second edition came out in 1713 under the editorship of Roger Coates, with the general scholium added at the end, and a third in 1726, and an English translation appeared 2 years after Newton's death, its reception divided along a fault that had nothing to do with the arithmetic. The mathematicians of the continent, Huygens and Leibniz among them, accepted the calculations and admired the mechanics, and objected that attraction across empty space, with no medium to carry it and no explanation of its cause, was a return to the occult qualities that the new philosophy had been at pains to expel. Newton did not claim to know the cause. In the general scholium, he wrote that he had not been able to deduce the reason for the properties of gravity from phenomena, and that he framed no hypotheses about it, and he let the law stand on the agreement between its consequences and the observed sky. In Britain, his authority grew steadily, helped by his position at the Mint, his long presidency of the Royal Society, and the deference of a generation of followers. And in France, the resistance held for some decades and then gave way, assisted by Voltaire's popular account and by the careful translation into French made by Émilie du Châtelet, which carried the Principia into a language where its consequences would be worked out for the next 100 years. The voyage that began the whole business had another purpose altogether. In 1672, the Académie des Sciences in Paris sent Jean Richet to Cayenne on the coast of South America to make astronomical observations at a station far from Europe, chiefly of Mars near its closest approach, so that the planet's position against the stars could be compared with measurements made in France and the scale of the solar system estimated from the difference. Richer carried instruments of the best available quality, among them a pendulum clock regulated in Paris to beat seconds, and once installed near the equator, the clock began to lose time, steadily and unmistakably, at a rate of the order of a couple of minutes each day. He checked it against the transits of stars, adjusted the pendulum until it beat true again, and found that he had to shorten the rod by a small but definite amount, a little over a line in the measure of the day, which is a fraction of a modern millimeter in the region of 2 or 3. He recorded the correction carefully, restored the original length when he returned to France, and confirmed that in Paris the longer pendulum was again correct. The finding was more interesting than a defect in a clock. Huygens had established that the period of a pendulum depends on its length and on the strength with which weight draws the bob downward, so that if the same pendulum swings more slowly in one place than another, the pull of gravity in the slower place must be weaker. Richer's clock therefore reported that a body near the equator weighs slightly less than the same body in Paris, by a difference of a few parts in 1,000, too small for any balance of the period to detect directly and yet perfectly legible in the counting of seconds over a day. Other observers, sent to other latitudes in the decades that followed, found the same pattern, with the second's pendulum growing shorter as one approached the equator and longer as one moved toward the poles, and by the end of the century, the variation of weight with latitude was accepted as a fact of nature awaiting an explanation. Two explanations offered themselves, and both turned out to be at work. The first was rotation. A body resting on the turning Earth is carried in a circle once a day, and part of its weight is spent in keeping it on that circle. The more so, the larger the circle, which is greatest at the equator and vanishes at the poles. The second was shape. If the Earth were a rotating fluid, it could not remain a sphere, since the same rotation that lightens bodies at the equator would allow the equatorial regions to stand higher, further from the center, where gravity is weaker still. Newton worked through this reasoning in the third book of the Principia, imagining a canal of water running from the pole to the equator through the interior and requiring that the two branches balance, and arrived at a flattening of about 1 part in 230, so that the diameter through the equator would exceed the diameter through the poles by roughly that fraction. Huygens, proceeding from a different assumption about how gravity acts within the body of the Earth, obtained a smaller flattening, but he agreed on its direction. The Earth was to be an oblate spheroid, wider than it was tall, and the length of a degree of latitude measured along a meridian ought to grow longer as one went north, since a flattened surface is less sharply curved near the poles. That prediction could be tested by surveying. The method had been established by Jean Picard, who in the years around 1670 measured an arc of the meridian north of Paris by laying out a baseline on level ground, extending it through a chain of triangles whose angles were read with telescopic sights, and fixing the latitudes at the two ends by observing stars near the zenith. Newton had used Picard's figure for the size of the Earth in his own calculations. The Paris Observatory, under Jean-Dominique Cassini and then his son Jacques, extended the survey the length of the kingdom from Dunkirk on the Channel to the Pyrenees, and when the results were reduced and published in the 1720s, they gave the opposite of what the theory required. The degrees appeared to grow shorter toward the north and longer toward the south, which would mean an Earth elongated at the poles, drawn out like an egg rather than pressed down like an orange. The disagreement was small in magnitude and large in consequence, since the whole of Newtonian attraction was implicated on one side and the measurements of the Royal Observatory on the other, and it settled into a quarrel that ran through the Academy for a decade, with the Cassinis and their allies defending the survey and a younger group, Maupertuis and Clairaut among them, defending the theory. The difference between the rival degrees amounted to a few hundred toises out of some 57,000, well within the reach of accumulated error over a chain of triangles 1,000 kilometers long, and the way to decide the matter was to measure arcs far apart in latitude, where the predicted difference would be large enough to survive the uncertainties. The Academy accordingly resolved to send 2 expeditions, one as near the equator as could be managed, and one as near the pole. The equatorial party left first, sailing in 1735 for the Spanish Viceroyalty of Peru in the highlands that are now Ecuador, with permission from the Spanish crown and 2 young Spanish naval officers, Jorge Juan and Antonio de Ulloa, attached to the company. The French members were Louis Gaudin, Pierre Bouguer, and Charles-Marie de la Condamine, together with a surgeon, a draftsman, a botanist, and assistants. Their arc ran south from near Quito along a corridor of high plateau between the two ranges of the Andes, and the work proved far harder than anything the method had faced in France. Signals had to be built on ridges at altitudes where snow and cloud closed in for weeks. Baselines measured on ground that was rarely level, angles read through air disturbed by heat, and the astronomical observations for latitude made with a long zenith sector that had to be carried up mountains and set truly vertical. The party was short of money, divided by personal quarrels, delayed by legal proceedings over the stone monuments they wished to leave to mark their baseline, and reduced by illness and by the death of the surgeon Seniergues in a riot at Cuenca. What had been planned as 3 years became nearly 10. The northern party was quicker. Maupertuis sailed in 1736 with Clairaut, Camus, Le Monnier, and the Abbé Outier, joined in Sweden by the astronomer Anders Celsius, and their arc was laid out along the valley of the Torne River in Lapland. Running inland from the head of the Gulf of Bothnia, they surveyed the triangles in the brief summer, working among mosquitoes and marsh, and measured the baseline in winter across the frozen river, where the ice offered a flat surface of the kind that had cost the Peruvian party so much labor to find. They were back in Paris by the autumn of 1737 with a degree of latitude distinctly longer than the corresponding degree in France, longer by more than the errors of the work could account for, and therefore in agreement with the flattened Earth. Maupertuis was celebrated for it, sat for a portrait with his hand resting on a globe pressed down at the pole, and was greeted by Voltaire as the man who had flattened both the Earth and the Cassines. The Peruvian measurements, when they were finally reduced, gave a degree shorter than the French one, and the 3 arcs together settled the shape beyond serious dispute. A fresh survey of the French meridian in the years around 1740 removed the error in the older work and brought it into line. Bouguer, still in the mountains, used the occasion for further studies of gravity itself, comparing pendulum rates at sea level and on the high plateau, and attempting to detect the sideways pull of the mountain Chimborazo on a plumb line, an experiment whose result was small and uncertain, but whose principle would be taken up again in Scotland a generation later. La Condamine came home by way of the Amazon, mapping the river as he descended it. Godin remained in Peru for years afterward. The flattening they had established was refined repeatedly through the following century, the Lapland figure in particular proving somewhat too large, and the measurement of the figure of the Earth became a permanent branch of science, the ground on which the meter would later be defined and on which every map of the world still rests. The suggestion that a mountain might be weighed against the whole Earth had been made long before anyone attempted it, since Newton himself had considered what would happen to a plumb line hung beside a large hill, and had concluded that the sideways pull of the hill would draw the line a little out of the vertical, by an amount so small that he doubted it could be measured with the instruments then available. The principle was simple enough to state. A plumb bob hangs along the direction of the total gravitational attraction acting on it, and if almost all of that attraction comes from the Earth beneath, while a small part comes from a mass of rock standing to one side, then the line will settle at a slight angle from the direction it would take on a featureless plane, and the size of that angle compares the mountain with the planet. Bouguer had tried it in the Andes, on the flank of Chimborazo, in conditions of cold and altitude that made steady observation nearly impossible. and had come away with the deflection that was smaller than his theory led him to expect, and burdened with uncertainties he did not attempt to conceal. The attempt was remembered in London, and in the early 1770s the Royal Society found itself with a sum of money left over from the expeditions it had sent out to observe the transits of Venus. Together with the Astronomer Royal, Neville Maskelyne, who thought the mountain experiment worth a proper trial in Britain. A committee was formed to consider the attraction of hills, Cavendish among its members, and the search began for a mountain of the right shape. What was wanted was an isolated hill, steep on two opposite sides, so that its mass would be concentrated close to the observing stations, regular enough in outline that its volume could be computed from a survey, and made of rock of reasonably uniform kind. Charles Mason, who had already spent years surveying in America, was engaged to travel through the north of England and Scotland looking for a suitable candidate, and he reported that Schiehallion in Perthshire came nearest to the requirements, a long whaleback ridge running east and west, rising steeply on its northern and southern flanks, standing well clear of its neighbours and composed of a hard grey rock. Mason declined the work of observing there, and Maskelyne, somewhat reluctantly, went himself. The plan was to establish two observing stations, one on the northern slope and one on the southern, as nearly as possible on the same meridian, and to determine the latitude of each by astronomy, measuring the zenith distances of stars as they crossed the meridian with a zenith sector, an instrument built for exactly that narrow purpose. The difference of the two astronomical latitudes gives the angle between the two local verticals. The distance between the stations, measured on the ground by triangulation, gives the difference of latitude that would be expected if the verticals were undisturbed. Any excess in the astronomical difference is the sum of the two deflections, the plumb line at the northern station being drawn southwards toward the hill, and the plumb line at the southern station being drawn northwards. Maskelyne spent the summer and autumn of 1774 on the mountain, living in a hut of turf and timber with his instruments in a small observatory nearby, assisted by Reuben Burrow and by a party of labourers who moved the sector, cut sightlines and carried out the survey. The weather was what the Western Highlands usually offer, so that clear meridian passages had to be gathered patiently between long stretches of mist and rain, and the work ran on for 4 months, while the same stars were observed again and again from each station in turn. The measurement of the distance between the two stations and the survey of the mountain's surface went on alongside the astronomy, with hundreds of triangulated points fixed on the slopes and summit. The result was a discrepancy of nearly 12 seconds of arc between the two ways of reckoning the difference of latitude, a quantity small in absolute terms and large in relation to the errors of the sector, and unmistakably in the direction the theory required. The plumb lines had been pulled toward the hill. That alone settled a question that had been raised in argument more than in earnest, namely whether the Earth might be hollow, since a hollow shell would attract far less than the solid globe and would make the mountain's relative pull much greater than what was found. It also showed, in a way no orbit could show, that the attraction described by Newton acted between ordinary parcels of rock, and not merely between planets and their satellites. Turning the 12 seconds into a density was the work of Charles Hutton, a mathematician at the Royal Military Academy, and it took him some years. He had to calculate the total attraction of the mountain on each station, which meant knowing the mountain's shape in detail. And to do that, he divided the surveyed heights into a grid, worked out the pull of each column of rock, and summed them. In the course of this reduction, he joined points of equal height with lines drawn across his plan, so that the shape of the ground could be read at a glance, and the practice of drawing contours on maps descends in part from that piece of arithmetic. Comparing the mountain's attraction with the Earth's and assuming a density for the rock of Schiehallion, he arrived at a mean density for the Earth of about 4.5 times that of water. The figure was later revised upward toward 5 times water when the rocks of the mountain were examined more carefully and found to be denser than Hutton had assumed. And when the geology of the hill turned out to be less uniform than the plan of the experiment had supposed. Hutton also noted what the number implied, since the rocks that people quarry and build with are between 2 and 3 times as dense as water, and a mean of 5 for the whole globe therefore requires the deep interior to be a great deal denser than anything at the surface. The end of the season on the mountain was marked by a celebration in the observer's hut, and the story preserved locally is that the building caught fire during it and that a fiddle belonging to one of the local men was lost in the blaze, a loss for which Maskelyne is said to have made amends with another instrument. The second approach to the same quantity dispensed with mountains altogether. John Michel, a Yorkshire clergyman who had thought carefully about gravitation and about the attraction of light by massive bodies, designed an apparatus in which 2 small lead balls hung from the ends of a light horizontal rod suspended at its middle by a slender wire, so that the smallest sideways force would twist the wire and turn the rod. Larger masses brought up beside the small balls would attract them, and the twist could be measured. Michel died in 1793 without having used the instrument. It passed to Francis John Hyde Wollaston, and from him to Henry Cavendish, who rebuilt it and set it up in a shuttered outbuilding at his house in Clapham. Cavendish worked with a wooden rod some 6 feet long, carrying lead balls about 2 inches across, enclosed in a narrow case to keep the air still, with 2 large lead spheres about 1 foot in diameter and weighing several hundred pounds each hung from a frame that could be swung into position from outside the room. The deflection he had to measure was a fraction of an inch, so he read the position of the rod through telescopes fixed in the wall of the shed, sighting on ivory scales inside the case, lit by lamps arranged so that no draught could reach the apparatus. He worked the frame carrying the large weights by cord and pulley from outside, so that neither his body heat nor his movement disturbed the balance, and he waited between readings for the slow swing of the rod to settle. To convert the deflection into a force he needed to know the stiffness of the suspending wire, and he obtained it by timing the period of the rod's free oscillation, since a rod that swings slowly hangs from a weak torsion and one that swings quickly from a stiff one. With the force known and the weights and separations known, he could compare the attraction of the large lead spheres for the small ones with the attraction of the Earth for the same small ones, which is simply their weight. The comparison gave the mean density of the Earth as about 5.5 times that of water, a value published in the Philosophical Transactions in 1798, close to what later and far more elaborate experiments would confirm, and reached in a garden shed with lead, wood, wire, and patience. Of all the effects that gravitation produces on the Earth, the one that ordinary life notices without instruments is the rise and fall of the sea, And it was to the tides that Newton turned in the third book of the Principia, in order to show that his attraction reached down into the water as well as out into the sky. The essential idea is that the moon does not pull equally on every part of the Earth, since the near side is closer to it than the center and the far side is further away, so that the water on the near side is drawn slightly more strongly than the solid globe beneath it, and the water on the far side slightly less, with the result that the ocean is stretched into a long shape with a bulge at each end, and the turning of the Earth beneath that stretched shell carries most coasts through 2 high waters and 2 low waters in a little over a day. The Sun does the same thing, and although it is vastly more massive than the Moon, it is also very much further away, and because the stretching depends on how sharply the pull changes across the width of the Earth, rather than on the strength of the pull itself, the solar tide comes out roughly half the size of the lunar one. That single circumstance accounts for the pattern that fishermen and harbor masters had known for centuries without being able to explain it. Namely that when the moon is new or full and lies in line with the sun, the 2 tides reinforce each other and the range is large, and when the moon stands at its quarters, the 2 work across each other and the range is small. Newton could therefore derive the fortnightly rhythm of spring and neap tides from the same law that held the moon in its path, and he attempted, from the observed heights, a rough estimate of the mass of the moon itself. What he could not do, and did not pretend to do, was predict the tide at any particular place. The equilibrium picture, in which the water settles instantly into the shape that the forces demand, describes an ocean covering a smooth globe to a uniform depth, whereas the actual ocean is interrupted by continents, shelves, straits and gulfs, and the tidal disturbance travels through it as a very long wave whose speed depends on the depth of the water. The consequence is that high water arrives at a port not when the moon is overhead, but at some fixed interval afterwards, an interval peculiar to that port, and that in some basins the wave finds a natural period close to that of the driving force and swells into ranges of many meters, while in others, such as much of the Mediterranean, it barely registers. The tide is therefore a local response to a universal cause and separating the 2 occupied observers for the next 2 centuries. While the water was being studied, the moon itself remained the harder problem, and here the work of Edmund Halley shows how the new mechanics began to reach backwards in time. Halley collected records of ancient eclipses drawn from Babylonian and Greek sources and from later Arabic astronomers, and compared the places and times they implied with the positions given by the tables of his own century. And he concluded that the moon was moving a little faster now than it had been then, an effect so gradual that it shows only across thousands of years. He also applied the same gravitational reasoning to comets, computing orbits from recorded observations and noticing that the comet seen in 1682 had appeared before at intervals of about 75 or 76 years, from which he suggested that it would return again around the middle of the following century, a return duly observed at the end of 1758. Some 16 years after his death. The refinement of that prediction was itself a piece of gravitational arithmetic, since a comet passing near Jupiter and Saturn is pulled off its ideal ellipse, and Alexis Clairaut undertook to calculate how much those 2 planets would delay the comet's arrival, publishing a corrected date shortly before the object was found. Clairaut had already worked on a more delicate matter, the slow turning of the Moon's orbit, whose long axis swings around in about 9 years. The first approximate treatments gave only half the observed rate, which for a time looked like a genuine failure of the inverse square law, until Clairaut carried the approximation further and found that the neglected terms supplied the missing half. The law had not failed. The mathematics had merely been stopped too soon. That episode set the pattern for the whole of the next century, in which gravitation was tested less by new experiments than by longer and more careful calculation. Leonhard Euler devoted much of his working life to the motion of the Moon, developing methods for handling the mutual attraction of 3 bodies that no one could solve exactly, and producing successive lunar theories in which the position of the Moon was expressed as a long sum of periodic corrections, each with its own amplitude and period, added to a simple elliptical motion. The practical value of such work lay at sea, because a navigator who knows the Moon's predicted position among the stars and can measure its actual angular distance from a star has, in effect, a clock in the sky, and can determine longitude without carrying a timekeeper. Lunar tables built on these methods, notably those of Tobias Mayer, were tested by the British authorities concerned with the longitude problem and became the basis of the published almanacs, and the awards made for them recognized both the tables and the analysis underlying them. The synthesis of this long effort belongs to Pierre-Simon Laplace, who gathered the results of a century of celestial mechanics into the volumes of the Mécanique Céleste, published between the closing years of the 1700s and the 1820s. Among the problems he settled was one that had troubled astronomers since Halley's time: the apparent drift of Jupiter and Saturn from their tabulated places, Jupiter running ahead and Saturn falling behind over intervals of many decades. Laplace showed that this so-called great inequality arose because 5 orbits of Jupiter come close to matching 2 orbits of Saturn, so that their small mutual pulls, instead of averaging away, accumulate in the same sense for a very long time before reversing, producing a swing with a period of roughly 900 years. The planets were not straying. They were exchanging influence on a schedule longer than the history of the observations. Laplace applied the same reasoning to the Moon's slow acceleration, attributing it to the gradual change in the shape of the Earth's orbit and the consequent change in the average solar disturbance of the Moon, a result that seemed to complete the demonstration that the solar system needed no external repair. In the middle of the following century, that account was found to be incomplete, since the calculation contained an error of magnitude, and the gravitational term explains only part of the observed change, the remainder coming from the friction of the tides themselves, which slowly slows the rotation of the Earth and, through the exchange of angular momentum, alters the Moon's motion. The tides in the lunar orbit thus turned out to be 2 faces of one process, though that recognition came later. Laplace also gave the tides their proper mechanical treatment, setting aside the equilibrium picture and writing equations for the motion of a shallow layer of water on a rotating globe under a periodic force, which is the beginning of the dynamic theory still in use. From that theory came the understanding that tides are best described not as one wave, but as a sum of many, each with a period fixed by astronomy, some daily, some twice daily, some fortnightly, monthly or yearly, and each with an amplitude and a delay determined by the local basin. The heights and times at a given port could then be found by measuring those local constants from a record of the water level and using them to project the same combination forward. The projection was laborious, since summing a dozen or more slow oscillations for every hour of a year is arithmetic without end, and so the summation was given to machinery. William Thomson, later Lord Kelvin, designed an apparatus in which each tidal constituent was represented by a pulley carried on a rotating crank, with a single wire passing over all of them, so that its total displacement was the sum of the separate motions, and a pen at the end of the wire drew the predicted curve on a moving drum as the machine was turned by hand. Later instruments, built in Britain and in the United States, added more constituents, dozens in the larger machines, and produced a year of tide tables in a matter of hours. They remained in service well into the 20th century, and the tables they printed guided harbour traffic, dredging, engineering works, and the timing of amphibious landings in war. All of it the visible residue of an attraction between masses that no one has ever seen directly. The planet that made the calculation necessary had itself been found by accident. William Herschel, sweeping the sky from a garden in Bath with a telescope of his own making, noted on the 13th of March, 1781, an object that showed a small disk rather than a point, and took it at first for a comet. Within months, the smoothness of its motion and the shape of its path had shown it to be a planet moving far beyond Saturn in an orbit of some 84 years. Once its elements were roughly known, astronomers went back through the older records and found that it had been seen before and mistaken for a star. Entered in the catalogue of John Flamsteed near the end of the 17th century and observed several times in the 1760s by Pierre-Charles Lemonnier in Paris, who had not noticed that the star shifted from night to night. These old sightings were a gift to the theorists because a planet with an orbit of 84 years takes a very long time to reveal the shape of its motion, and the accidental observations extended the record backwards by nearly a century before anyone knew what they were looking at. They also introduced a difficulty. When Alexis Bouvard, who had worked with Laplace on the perturbation calculations for Jupiter and Saturn, drew up new tables for Uranus in 1821, he found that he could fit the modern observations or the ancient ones, but not both together with the same set of orbital elements. Choosing to trust the recent measurements, which were made with better instruments and by observers who knew they were watching a planet, he set the older ones aside and remarked in print that some foreign influence might be acting on the body, leaving the question to later work. Within 2 decades, the tables built on the modern observations had themselves drifted, so that the planet's computed longitude and its observed longitude parted company by an amount that grew year on year, reaching a discrepancy of well over a minute of arc, which is small on the sky and enormous by the standards of gravitational astronomy, where agreement to a few seconds of arc had come to be expected. Several astronomers considered the possibility of a further planet, and 2 men set about the calculation in earnest. John Couch Adams, a young Cambridge graduate, began in the early 1840s to treat the residuals in the motion of Uranus as the signature of an unseen body, assuming for simplicity that it lay roughly twice as far from the Sun as Uranus, in accordance with the rough regularity of planetary spacings then in fashion, and solving for the mass and orbital position that would best reproduce the errors. By the autumn of 1845, he had a predicted place, which he communicated to George Biddell Airy, the Astronomer Royal, and to James Chalice, the director of the Cambridge Observatory. Airy replied with a question about the planet's distance from the Sun, a technical point on which he wished to satisfy himself, and Adams, for reasons that were later much discussed and never fully explained, did not answer it promptly, so that the matter rested. In Paris, Urbain Jean-Joseph Leverrier had taken up the same problem, apparently without knowledge of Adams, and pursued it with a thoroughness that filled a series of memoirs presented to the Academy of Sciences in 1845 and 1846. He began by establishing that no adjustment of the known planets could remove the discrepancies, then showed that the residuals were consistent with the action of a single exterior body, and finally, in the summer of 1846, gave a specific longitude at which the planet should be found, together with an estimate of its mass and a note that it should show a disk large enough to be distinguished from a star in a good telescope. The French observatories were slow to look. Leverrier, impatient, wrote to Johann Gottfried Galle at the Berlin Observatory, who had recently sent him a copy of a dissertation and to whom he could therefore address a request without formality, asking that the region be examined. The letter reached Berlin on the 23rd of September, 1846. Galle obtained permission to use the large refractor that evening, and with the assistance of a student, Heinrich Louis d'Arrest, adopted a method better suited to the task than direct inspection of disks. D'Arrest read out the positions of stars from a newly engraved chart of that part of the sky, while Galle called out what he saw at the eyepiece. Before long, Galle named a star of the 8th magnitude that d'Arrest could not find on the map, lying less than a degree from the place Leverrier had specified. The following night, the object had moved, by an amount consistent with a planet at that distance, and the identification was secure. Word traveled quickly, and observers elsewhere confirmed both the motion and the small disk. At Cambridge, Chalice had begun a search in the summer, working through a wide region star by star without a suitable chart, and discovered on reviewing his notes that he had recorded the planet twice in early August without recognizing that one of his points had shifted. The discovery was followed by a dispute over credit that occupied the scientific press of two countries for months, conducted with more heat by the partisans on each side than by the two calculators themselves, who met afterwards and remained on cordial terms. The convention that settled was to name both, and the planet, after proposals that included Janus, Oceanus, and the name of Leverrier himself, was called Neptune, in keeping with the mythological pattern of the older names. Later examination of early observing records turned up another instance of the planet having been seen and taken for a star, in notebooks kept in the years just after the invention of the telescope, when Neptune passed close to Jupiter and was drawn among the field stars by an observer watching the Jovian satellites. The mathematics of the prediction has been re-examined many times since, and the verdict is more mixed than the immediate triumph suggested. Both Adams and Leverrier had assumed an orbit considerably larger than the true one, following the spacing rule then current, and both arrived at masses too great and at orbital periods much longer than the 165 years Neptune actually takes. What they determined accurately was the direction in which the disturbing body then lay, which is the quantity to which the residuals in the motion of Uranus were most sensitive, and which happened at that epoch to be close to the truth for a range of assumed distances. Had the search been made a few decades earlier or later, the predicted longitude would have been substantially wrong. The result was sound in its method and fortunate in its timing, and the immediate effect on the standing of gravitational theory was very great, since the appearance of a new world at a computed place was the plainest confirmation that the inverse square law governed regions where nobody had yet looked. Leverrier turned next to the inner planets, and to Mercury in particular, whose orbit had long resisted exact representation. The long axis of that orbit rotates slowly in the plane of the sky, an advance of the perihelion amounting to somewhat more than 5,000 seconds of arc per century when reckoned against the equinox, and almost all of that motion could be accounted for by the precession of the terrestrial reference frame together with the pull of Venus, the Earth, Jupiter, and the rest. In a memoir of 1859, Leverrier reported that a residue remained, an unexplained advance of the perihelion of Mercury of a few tens of seconds of arc per century, small but well outside the uncertainty of the observations, which included a long series of transits of Mercury across the face of the Sun, timed with care since the 17th century. Simon Newcomb later reworked the whole calculation with improved data and fixed the residual at close to 43 seconds of arc per century, a figure that subsequent analyses have not substantially altered. Leverrier proposed the remedy that had served him before, namely unseen matter closer to the Sun than Mercury, whether a single planet or a ring of small bodies distributed near the plane of the ecliptic. A country physician in France reported having watched a small dark spot cross the solar disk, and the supposed planet was given the name Vulcan, and entered briefly into some tables and textbooks. Observers looked for it in the darkness of total solar eclipses and in the daytime sky near the Sun, and reports of sightings accumulated without any two of them agreeing well enough to fix an orbit. A ring of small bodies dense enough to turn Mercury's perihelion at the required rate would have added a detectable glow to the zodiacal light and would have disturbed the orbit of Venus as well, in ways that were not seen. Others tried altering the law itself, replacing the exponent 2 by a value very slightly larger, which could be tuned to fit Mercury, but then spoiled the agreement already achieved for the Moon and the other planets, or attributed the effect to a flattening of the Sun far greater than its measured shape allowed. Each proposal accounted for the one discrepancy and created others, and the anomaly stood in the tables for more than half a century, a small persistent excess in the turning of one orbit, recorded in seconds of arc and left without explanation. The resolution came from a direction that had nothing to do with Mercury. In the years after 1905, while working as an examiner of patent applications in Bern, and afterwards in the universities of Zurich, Prague, and Berlin, Albert Einstein returned repeatedly to a simple observation about falling, one he later described as the most fortunate thought of his life, namely that a person who falls freely does not feel their own weight. In freefall, the sensation of heaviness disappears entirely, and objects released alongside the falling observer hang motionless beside him, so that within the falling frame there is no local experiment that distinguishes the situation from rest in empty space, far from any attracting body. The converse followed as well, For an observer in a sealed chamber accelerated steadily through empty space would find that released objects drifted to the floor with equal accelerations, exactly as they do on the surface of the Earth. This equality of gravitation and acceleration, which Einstein raised to a principle, rested on the very fact that Galileo had established with his inclined planes, and that Newton had built into his equations without explaining, that all bodies fall alike regardless of their substance or their weight. From this principle, certain consequences could be drawn before any full theory existed. In a paper of 1911, Einstein argued that light climbing away from a massive body must be shifted toward the red end of the spectrum, its oscillations counted as slower by a distant observer, and that a ray of light passing near the sun must be bent from a straight path, since a beam crossing an accelerating chamber traces a curve on the far wall. The deflection he calculated then, a little under 9/10 of a second of arc for a ray grazing the solar limb, turned out to be half the correct figure, because the argument accounted for the effect of gravitation on time but not yet on the geometry of space. Working out the full theory occupied him for most of the following 4 years, in collaboration for a time with the mathematician Marcel Grossmann, who introduced him to the absolute differential calculus developed by Gregorio Ricci Curbastro and Tullio Levi-Civita, itself built on the geometry of curved spaces set out by Bernhard Riemann in the middle of the previous century. The path was not direct. Einstein adopted and then abandoned candidate equations, published arguments he later withdrew, and in November of 1915 presented to the Prussian Academy in a series of short communications the field equations in their final form, relating the curvature of a four-dimensional space-time to the distribution of matter and energy within it. In the same series, he applied the new equations to the motion of a planet in the field of the Sun and found that the orbit did not close upon itself but turned slowly in its plane, and that the rate of turning for Mercury came out at 43 seconds of arc per century, agreeing with the residue Leverrier had reported and Newcomb had refined. Nothing in the derivation had been adjusted to produce that number. The same equations doubled the predicted deflection of starlight to about 1 3/4 of a second of arc at the solar limb, a quantity within reach of photographic astronomy, though it could only be measured during a total eclipse, when stars close in angle to the sun become visible for a few minutes. The war delayed any test, and the Dutch astronomer Willem de Sitter and the English astronomer Arthur Eddington carried news and copies of the theory across the lines of the conflict through neutral Holland. The eclipse of the 29th of May in 1919 was well suited to the purpose, since the darkened sun would stand against the Hyades, a cluster rich in reasonably bright stars. Under the direction of Frank Watson Dyson, the astronomer royal, 2 expeditions were sent out, one to Sobral in the north of Brazil and one to the island of Principe in the Gulf of Guinea, where Eddington himself observed through gaps in the cloud. The measurement was delicate, since it required comparing star positions on eclipse plates with positions on plates of the same field taken months apart, at a different temperature and with the instrument in a different state. And one of the Sobral instruments produced images that had evidently been affected by the heat of the day. The results announced at a joint meeting of the Royal Society and the Royal Astronomical Society in November of that year favored the larger deflection over both the smaller Newtonian value and zero, with uncertainties that were considerable, and the newspapers of London and New York carried the finding as a revision of the Newtonian world. Later eclipse work through the following decades improved the figures slowly and with difficulty, and it was not photography of stars but radio interferometry, decades afterwards, using quasars whose positions could be measured as the sun passed near them, that fixed the deflection to a fraction of a percent of the predicted value. The other early prediction, the reddening of light escaping a gravitational field, proved harder to isolate in starlight, where the motions of the emitting gas produce shifts of a similar size. It was settled in a laboratory rather than an observatory when Robert Pound and Glenn Rebka, working at Harvard at the end of the 1950s, sent gamma rays from a radioactive iron source up and down a tower of some 22 meters and detected the minute change in frequency by the way the radiation was absorbed at the far end. Later measurements with atomic clocks flown in aircraft and carried on rockets confirmed the same effect with greater precision, and the running of clocks at different heights is now a routine correction in satellite navigation, where the timing signals from orbit would drift by tens of microseconds a day if the relativistic terms were omitted. Further tests accumulated through the second half of the 20th century. Erwin Shapiro pointed out that radar signals passing near the Sun should be delayed, their round trip lengthened by the curvature of space-time along the path, and echoes from Venus and Mercury, and later timing signals from spacecraft, including the landers on Mars, showed the delay at the predicted magnitude. Laser pulses returned from reflector arrays left on the lunar surface fixed the distance to the Moon to within centimeters and tested whether the Earth and the Moon fall toward the Sun at the same rate, as the equivalence principle requires. A satellite carrying 4 precisely spherical quartz gyroscopes, launched in 2004 and reported on some 7 years later, detected the small precessions that the theory predicts for a spinning body in orbit, including the slight dragging of the local inertial frame by the rotation of the Earth itself. The theory also predicted that accelerating masses would radiate, sending out ripples of curvature that travel at the speed of light and carry energy away from their source. Einstein derived this in the years just after the field equations and remained uncertain for decades whether the waves were physical or an artifact of coordinates. The first evidence came from a binary pulsar found in 1974 by Russell Hulse and Joseph Taylor, a pair of compact stars whose orbital period could be timed to remarkable accuracy through the arrival of radio pulses, and which was seen to be shrinking slowly at the rate expected if the system were losing energy to gravitational radiation. Direct detection required interferometers with arms kilometers long, in which laser light is used to compare the lengths of 2 perpendicular paths to a precision far smaller than the width of a proton. In September of 2015, the 2 instruments of the Laser Interferometer Gravitational Wave Observatory in Louisiana and in Washington State registered a brief rising signal consistent with the merger of 2 black holes of a few tens of solar masses at a distance of something over 1 billion light-years. And the result was announced the following February. 2 years later, a signal from the merger of 2 neutron stars was followed within seconds by a burst of gamma rays, and within days by telescopes across the spectrum, tying the waves to a visible event in a distant galaxy. On the largest scales, gravitation is now read from the shapes of images rather than from the motions of individual bodies. Light from remote galaxies passing through the mass of an intervening cluster is bent into arcs, rings, and multiple copies, and the pattern of that distortion maps the distribution of matter along the line of sight, most of which does not emit light at all. We are going to stop here. The music will carry on for a while, and then it will fade on its own. There is nothing more to do tonight. Rest well and see you very soon.